Multiverse scientists deviate from the long-standing scientific method, grounded in predictions and observations, by positing infinitely many unobservable parallel universes to explain fine-tuning.
Multiverse scientists have subtly switched to a mathematically formulated philosophical theory about an infinite multiverse in order to explain the fine-tuning of our one-ordered universe.
We'll justify through clear reasoning that the multiverse is not science, and will support this assertion through the words of prominent scientists who attempt to defend the esteem of science from multiverse's corrosive effects.
As we discussed last time, the scientific method of prediction, testing, and observation allows scientists to accept seemingly crazy theories like quantum mechanics. Without the scientific method, no one would accept such a wild theory based on philosophical speculation alone.
To some degree, multiverse scientists know that positing an infinite number of unobservable universes where everything possible happens sounds like a wild and crazy philosophical theory. They know that an infinite varied multiverse certainly isn't indicated by our observation of one fine-tuned universe with fixed laws and constants. They also know that there's no indication whatsoever for the hypothetical measure or meta-law that determines probabilities of different types of universes in the multiverse.
For all these reasons, multiverse scientists generally don't justify multiverse by claiming it's good philosophy. Instead, they insist that multiverse is science. To justify this claim, they note that inflation and string theory, the theories they use to support multiverse's first two premises, aren't science-based philosophical theories, but are rather bona fide scientific theories. And since these two scientific theories lead to an infinite varied multiverse, they argue that multiverse itself is legitimate science.
Even though, for the purpose of our argument, we temporarily accepted multiverse scientists' assumption that eternal inflation and string theory provide solid scientific justification for their first two premises, today we'll revisit this assumption in light of last episode's discussion of the scientific and philosophical methods.
Let's begin with premise one, that there exists an infinite number of other universes, and its support from the theory of inflation. As we explained in episode 3, the theory of inflation, the theory that the universe underwent a period of rapid expansion immediately after the Big Bang, seems to be a bona fide scientific theory, as it makes real predictions, some of which have been confirmed by observations. And since the simplest way to model inflation leads to eternal inflation and an infinite number of universes, multiverse scientists claim that science indicates the existence of an infinite number of universes.
But things aren't that simple. The problem is that eternal inflation's infinities render inflation incapable of making any predictions whatsoever. As we explained in episode 9, given an infinite number of universes where everything possible happens, there's no straightforward way of making a clear, unambiguous prediction to test whether or not eternal inflation corresponds to our observations. Without this essential element of the scientific method, it's impossible to say that eternal inflation is science.
The following quote from physicist Paul Steinhardt, one of the originators of the theory of inflation, explains what made him reject inflation altogether and instead look for a different theory. The context of the quote was an erroneous 2014 announcement of the discovery of primordial gravitational waves.
Well, it's not relevant to our discussion what these are. The point is that this discovery, if it were true, would have allegedly provided evidence for the theory of inflation, while simultaneously contradicting Steinhardt's own theory, a theory that we'll discuss at the end of this series. Despite the initial widespread excitement about this evidence, scientists quickly realized that the announcement was presumptuous. The data could be explained just as well by something as mundane as cosmic dust.
Steinhardt, in his 2014 Nature article, Big Bang Blunder Burst the Multiverse Bubble, discusses the aftermath of the announcement and its subsequent retraction as follows. The Bicep 2 incident has also revealed the truth about inflationary theory. The common view is that it is a highly predictive theory. If that was the case, and the detection of gravitational waves was the smoking gun proof of inflation, one would think that non-detection means that the theory fails. Such is the nature of normal science. Yet some proponents of inflation who celebrated the Bicep 2 announcement already insist that the theory is equally valid whether or not gravitational waves are detected. How is this possible? The answer given by proponents is alarming. The inflationary paradigm is so flexible that it is immune to experimental and observational tests. First, inflation is driven by a hypothetical scalar field, the inflaton, which has properties that can be adjusted to produce effectively any outcome. Second, inflation does not end with a universe with uniform properties, but almost inevitably leads to a multiverse with an infinite number of bubbles, in which the cosmic and physical properties vary from bubble to bubble. The part of the multiverse that we observe corresponds to a piece of just one such bubble. Scanning over all possible bubbles in the multiverse, everything that can physically happen does happen an infinite number of times. No experiment can rule out a theory that allows for all possible outcomes. Hence, the paradigm of inflation is unfalsifiable. This may seem confusing given the hundreds of theoretical papers on the predictions of this or that inflationary model. What these papers typically fail to acknowledge is that they ignore the multiverse, and that, even with this unjustified choice, there exists a spectrum of other models which produce all manner of diverse cosmological outcomes. Taking this into account, it is clear that the inflationary paradigm is fundamentally untestable and hence scientifically meaningless.
So, while inflation started off looking like an ordinary scientific theory capable of making real predictions, over time, physicists realized that the simplest models of inflation naturally lead to an infinite multiverse, incapable of making any predictions, primarily because of the infinities and the measure problem. This led scientists like Steinhardt to reject inflation entirely and to search for new scientific solutions to the original problems that inflation was intended to solve.
So while we initially credited multiverse scientists with supporting the infinite multiverse premise with the scientific theory of inflation, once you take into account the infinities of eternal inflation, it becomes clear that inflation lacks the essential criteria of testing and falsifiability. This makes eternal inflation multiverse scientists' only real support for their first premise, unable to be verified using the scientific method.
Let's now look at string theory, the primary scientific justification for multiverse's second premise, that the constants vary from universe to universe. Multiverse scientists claim that the different possible configurations of string theory's unobservable hidden dimensions result in the fact that the values of the constants aren't truly constant, but are different in each universe. To evaluate the truth of this claim, we must ask, is string theory a good scientific theory?
Well, that's a controversial question. String theory is a 40-year-old theory with a beautiful mathematical formulation, but no experimental support. To date, it has made no testable predictions by which we can determine if it's true or false. Nevertheless, string theorists hope that one day string theory will make a testable prediction.
Unfortunately, it's unknown how long this will take. One could very well argue, and some scientists like Lee Smolin do, that 40 years has been long enough. But since there's no hard and fast rule for how much time to give a theory to make a prediction, if the entire issue were just a matter of time, it would be reasonable to provisionally grant string theory the status of a scientific theory, while we wait for it to make a prediction.
But it's no longer just a question of time. There seems to be an absence of expected evidence that indicates string theory is not true. String theorists attempted to use an indirect method to support string theory by observing some of its key features, like hidden dimensions or supersymmetry. They had hoped and expected that the Large Hadron Collider at CERN would find evidence to support these features of string theory. But these attempts came up empty. They simply didn't find what would be expected if string theory were true. Of course, that still didn't completely falsify string theory because its predictions can be tweaked after the fact to justify why nothing showed up.
Aaron, I'm going to pretend you didn't just throw in the word supersymmetry, and I'll assume our listeners don't need to know what that is. The main point is that certain features about the universe that string theory predicts to exist were anticipated to be observed at CERN, and they weren't. While this doesn't quite disprove string theory, it's a serious problem.
Right. The absence of evidence is a problem for a theory when scientists would expect that evidence to be seen. The past decade's failure to observe anything at CERN that supports string theory has dealt a major blow to string theory and is a significant reason why it's become much less popular as of late.
But the story is much worse for string theory than the mere absence of anticipated evidence. There is good reason to believe that string theory will never be able to make a clear, unambiguous prediction that will actually put string theory to the test.
Recall that in order to justify that the constants vary and thereby explain fine-tuning, string theory needed the 10 to the 500 different possible configurations of the string theory landscape. But once we consider the fact that string theory has 10 to the 500 different versions, it becomes nearly impossible to ever test it. No matter what experimental result you would ever find, string theorists could always just claim that that result corresponds to a different one of the 10 to the 500 different versions of the theory.
To highlight the point that because the string theory landscape is so vast, it's assumed that it can explain any result, consider the fact that string theorists don't even know if the values of the constants in our universe correspond to one of the 10 to the 500 different configurations. Nevertheless, they still believe that our universe is probably somewhere in the vast string theory landscape. As Brian Greene wrote, to date, no one has found an example that reproduces the features of our universe exactly. But with some 10 to the 500 possibilities awaiting exploration, the consensus is that our universe has a home somewhere in the landscape.
This shows that no matter what observation physicists will ever make, someone will be able to claim that it's potentially true for at least one of the 10 to the 500 different configurations that are still awaiting exploration. Because of this, it's unreasonable to expect that string theory will ever be subject to a credible scientific test. In this spirit, Peter Woit, in his 2006 book, Not Even Wrong, writes as follows. The possible existence of, say, 10 to the 500 consistent different vacuum states for superstring theory probably destroys the hope of using the theory to predict anything. If one picks among this large set just those states whose properties agree with present experimental observations, it is likely there still will be such a large number of these that one can get just about whatever value one wants for the results of any new observation. If this is the case, the theory can never predict anything and can never be falsified.
Putting it all together, string theory, which is multiverse scientists' only real support for the second premise, has never made a testable prediction. And because of the 10 to the 500 different configurations, all indications are that it never will. Furthermore, experimental results from CERN over the past decade have dashed the hope of observing some of string theory's more exotic features. As a result, multiverse scientists don't have any valid scientific justification for their second premise. That is, even if unobservable universes do exist, there is no scientific evidence to suggest that they have different laws or constants.
We've shown that eternal inflation and string theory, multiverse scientists' supports for their first two premises, both fail to be true scientific theories. You may think that this is merely a failure of the eternal inflation string theory multiverse, but this isn't the case. The inability to make a genuine prediction is characteristic of all multiverse theories.
No multiverse theory has ever made any new prediction besides the mundane prediction that we should expect to observe ourselves in the typical universe. Meaning, multiverse's one prediction is that we should observe everything we already know to be true. And because of episode 8's Boltzmann brain and grand universe problems, even that prediction isn't true.
To rescue the multiverse as science, some suggest that they need more time for the multiverse to make a genuine prediction. But even multiverse scientists admit they have no idea when that will be. As we mentioned last time, Brian Greene writes, no one knows whether it will take years, decades, or even longer for observational and theoretical progress to extract detailed predictions from any given multiverse.
But once again, waiting won't help. The problem for multiverse is deeper than just having to wait a long time for a prediction. Due to the infinities inherent in the multiverse and the associated measure problem we discussed in episode 10, there is simply no way that any infinite varied multiverse theory will ever be able to make a real prediction. As such, while multiverse certainly shouldn't be considered genuine science, it shouldn't even be labeled provisional science. Rather, it should be identified for what it truly is: poor speculative philosophy.
It shouldn't be surprising that a theory about an infinite number of unobservable universes doesn't meet the high standards of the scientific method. Instead of viewing this as a failure of the multiverse, we should actually view it as a triumph of the scientific method in weeding out wild speculative theories with no actual predictions or observations to support them.
This brings us to the last remaining solution multiverse theorists propose to rescue the multiverse as a scientific theory: changing the definition of science. Let's begin with the conventional definition of the scientific method from the Oxford English Dictionary as, quote, a method or procedure that has characterized natural science since the 17th century, consisting in systematic observation, measurement, and experiment, and the formulation, testing, and modification of hypotheses.
Some multiverse theorists have suggested that the definition of science be changed so that theories can still be considered scientific even if they don't make predictions that allow them to be falsified. This suggestion takes one of two forms. The first calls for a new, updated definition of science to reflect a new reality, while the second argues that science never really included the requirement of predictions, testing, and falsifiability in the first place.
Let's examine these two approaches. An example of the first can be found in the Astronomy and Geophysics article, Universe or Multiverse, which weighs arguments for and against the multiverse and its place in science. Physicists Bernard Carr, for, and George Ellis, against, consider the claim that, quote, the nature of science changes, so it is illegitimate science today may be legitimate tomorrow.
In defending the multiverse despite its lack of falsifiability, Carr argues as follows. George places a lot of emphasis on falsifiability, but not everybody in the philosophy of science agrees with Popper on this, and it is surely dangerous to impose a philosophical prescription that prevents scientists changing the border of their field. As Susskind cautions, it will be a pity to miss out on some fundamental truth because of an over-restrictive definition of science.
While Carr expresses the sentiment of those who suggest changing the traditional definition of science, physicist Sean Carroll takes the second approach. In his article, Beyond Falsifiability, Normal Science in a Multiverse, he argues that the standard definition of science that includes falsifiability was always a mistake. While many scientists of the past generation thought this was an essential element in the scientific method, Carroll claims that's not how science is actually done.
Carroll argues that scientists generally accept something as scientific if it meets criteria suggested by philosopher of science Thomas Kuhn, such as accuracy, consistency, broad scope, simplicity, and fruitfulness. He argues that even if it's impossible to ever test whether the multiverse is true or false, Kuhn's criteria can allow us to use abduction, reasoning to the best explanation, to infer that the multiverse is the best possible explanation for all our observations. He writes as follows. Multiverse models are scientific in an utterly conventional sense. They describe definite physical situations and are ultimately judged on their ability to provide an explanation for data collected in observations and experiments. But the kind of science they are is perfectly ordinary science. The ways in which we evaluate the multiverse as a scientific hypothesis are precisely the ways in which hypotheses have always been judged. The point is not that we are changing the nature of science by allowing unfalsifiable hypotheses into our purview. The point is that falsifiability was never the way that scientific theories were judged, although scientists have often talked as if it were.
Wait, Aaron, I thought that multiverse hadn't been verified through any experiments. So how does Carroll say that both the multiverse and ordinary science are ultimately judged on their ability to provide an explanation for data collected in observations and experiments?
Good catch, Ellie. Carroll doesn't mean that some experiments and observations actually test for the multiverse. That's clearly not true. All he means is that, since God is not a possible explanation for anything, the multiverse is the best way to explain our current experiments and observations. For example, Carroll mentions the measurement of the tiny value of the cosmological constant, which shows that it's fine-tuned. That's not an experimental test for the truth of multiverse. It's just that Carroll thinks the multiverse is the best way to explain the experiments that show fine-tuning.
The bottom line is that there are two approaches to redefining science. Either updating it to eliminate the requirement of prediction, testing, and falsifiability, or claiming that those criteria were never essential parts of the scientific method to begin with.
While some multiverse scientists advocate dropping testing and falsifiability from the accepted definition of science, numerous prominent scientists strongly disagree. This sentiment was clearly expressed by physicist Lee Smolin, one of the most vocal critics of both string theory and the multiverse. In his book, The Trouble with Physics, he wrote as follows. A theory has failed to make any prediction by which it can be tested, and some of its proponents, rather than admitting that, are seeking leave to change the rules so that their theory will not need to pass the usual tests we impose on scientific ideas. It seems rational to deny this request and insist that we should not change the rules of science just to save a theory that has failed to fulfill the expectations we originally had for it. If string theory makes no unique predictions for experiments, and explains nothing about the standard model of particle physics, which was previously mysterious, Apart from the obvious statement that we must live in a universe where we can live, it does not seem to have turned out to be a very good theory. The history of science has seen a lot of initially promising theories fail. Why is this not another such case?
While Smolin's point is controversial among contemporary scientists, all the great scientists of prior generations agreed that the heart and soul of the scientific method is the comparison of theory to observation. As Richard Feynman said, quote, "All scientists will agree that a question, any question, philosophical or other, which cannot be put into the form that can be tested by experiment, or in simple terms, that cannot be put into the form, if I do this, what will happen, is not a scientific question. It is outside the realm of science."
Even if multiverse scientists succeeded in convincing the people at Oxford to change the long-standing definition of science, it still wouldn't help them. The reason we grant esteem and validity to scientific theories is not because we collectively decide to call them science, but because they emerge from the scientific method of prediction, testing, and falsifiability. And since the multiverse doesn't emerge from this method, it doesn't matter what you call it.
This point was clearly stated by physicist George Ellis, who vehemently opposes Carr's suggestion to change the definition of science. Ellis articulated the great harm to science that would follow in the wake of such a change. In the above-mentioned article, he argues as follows. The foundations must be respected if one is to preserve the core features of science that have led to its phenomenal success. That is, the feedback from reality to theory provided by experiment and observational testing. One abandons that at one's peril. It is dangerous to weaken the grounds of scientific proof in order to include multiverses under the mantle of tested science. It is a retrograde step towards the claim that we can establish the nature of the universe by pure thought without having to confirm our theories by observational or experimental tests. This abandons the key principle that has led to the extraordinary success of science. The claim that multiverse exists is a belief rather than an established scientific fact.
Notice how Ellis uses strong words like dangerous and peril. Removing an essential feature of the scientific method will have many harmful consequences for the entire scientific enterprise. This is because the requirement of experimental verification has given science significant advantages over other fields of study.
Here are 3 advantages conferred on science by prediction, testing, and falsifiability. 1. They have allowed scientific consensus to form in all branches of science. 2. They've allowed scientists to reject false theories despite their appeal. And 3. They've allowed scientists to accept seemingly crazy theories like quantum mechanics.
Whether you change the definition of science going forward, like Carr suggests, or whether you argue, as Carroll does, that prediction, testing, and falsifiability were never really as essential as everyone thought, once you change the traditional definition of science, you lose all these benefits.
1. You lose the ability to build scientific consensus, as evidenced by the lack of consensus surrounding the multiverse. 2. You lose the ability to sniff out and undermine false theories, opening the door of the newly redefined science to beliefs like astrology, magic, and superstition. And 3. You lose the ability to verify and accept theories that seem wild and crazy.
This third point is critical to our argument. Without prediction, testing, and falsifiability, you lose the ability to verify and accept theories that you would never otherwise consider. Multiverse scientists can't change the rules and methodology of science while simultaneously holding on to a wild and crazy theory like the multiverse. The only reason we would consider it in the first place is because we rely on testing to confirm or disprove it. Once the scientific demand for experimental verification is dropped, ungrounded theories of unobservable parallel universes, reminiscent of the Twilight Zone, must be dropped as well.
Instead of trying to change the definition of science, multiverse scientists should just recognize that they are multiverse philosophers, not scientists. And once they do that, they need to evaluate the multiverse using proper philosophical methods. As Ellis writes in his 2011 Scientific American article, "Does the multiverse really exist?" Quote, "Nothing is wrong with scientifically based philosophical speculation," which is what multiverse proposals are, but we should name it for what it is.
It's crucial to differentiate between science and science-based philosophy. The division of natural philosophy into the 2 separate domains of science and philosophy that occurred around the time of Galileo and Newton was the foundational step that gave rise to modern science and greatly improved both areas of knowledge. If one removes the foundational principle of the scientific method and the rigor it provides, then the entire scientific enterprise that rests upon it crumbles as well. To confuse the two areas of thought in a speculative theory of an infinite varied multiverse is to do injury to both science and philosophy.
Despite its clear lack of experimental verification, multiverse scientists are loath to admit that the multiverse is science-based philosophy and not science. A contributing factor may be that many contemporary scientists don't appreciate the significant value of good philosophy. In fact, some even have an attitude of disdain towards all philosophy.
Consider the opening paragraphs of Stephen Hawking's book, The Grand Design. What is the nature of reality? Where did all of this come from? Did the universe need a creator? Traditionally, these are questions for philosophy, but philosophy is dead. Philosophy has not kept up with modern developments in science, particularly physics. Scientists have become the bearers of the torch of discovery in our quest for knowledge.
This disdainful attitude towards philosophy is relatively recent. Many of the great scientists of prior generations were well educated in philosophy and rightly regarded it as an essential field of study. You don't have to go back to Bacon, Galileo, and Newton. Even the great scientists of the 20th century, such as Einstein, Bohr, and Heisenberg, were deeply knowledgeable in philosophy and treated it with tremendous respect.
While Karin Susskind cautioned that it would be a pity to miss out on some fundamental truth because of an over-restrictive definition of science, this stems from the belief that all fundamental truths are exclusively scientific. We would argue instead that multiverse scientists don't have to miss out on any fundamental truths. All they need to do is to recognize that while science is wonderful, not everything true is science. There are fundamental philosophical truths as well.
Besides the intrinsic mistake of altering the definition of science, such a change would also bring harmful consequences to the entire scientific enterprise, and by extension to society as a whole. The reason is as follows. Once a theory is certified as science, it's accorded an esteem and validity that it wouldn't have otherwise. But is this esteem for science justified?
It depends. If scientists only certify theories that are legitimate science, then the label of science rightfully carries credibility and validity. However, if scientists improperly certify theories that should not be classified as science, that creates a real problem. It becomes impossible for the layperson to differentiate between actual science and counterfeit science, thereby undermining the credibility of genuine science.
This situation can be compared to a company that certifies metals they determine to be pure gold. If it only certifies genuine gold, then its certificate of authenticity has credibility. However, if it sometimes certifies fool's gold, pyrite, as genuine gold, then we can no longer trust its certification. We have no way to distinguish genuine gold from an imposter. And, of course, changing the definition of gold to include fool's gold won't be of any help.
Likewise, changing the definition of science to include untestable theories is merely a word game that will only succeed in undermining public confidence in all scientific theories. If multiverse theory doesn't truly deserve to be called science, but is nevertheless certified as such, this would undermine the trust and credibility of all the other theories that are rightfully certified as science. In this unfortunate case, the layperson would have no way of determining which theories truly deserve the esteem and validity of science and which are imposters.
This would be a disaster for everyone, not just the scientific community. For example, if people lose trust in science, they will be less likely to follow scientists' guidance to perform socially beneficial activities, like vaccination or conserving the environment.
Besides the practical benefits, trustworthy scientific knowledge is valuable to everyone. Scientific knowledge reveals the great wisdom throughout the universe and directs a person to the intelligent cause behind it all.
And appreciating science isn't just for religious people. Who isn't awed and inspired by the great discoveries of the scientific era, like the wonder and grandeur of the expanding cosmos, or the amazing molecular machinery in all living creatures?
Since having a clear body of knowledge that's accurately certified as genuine science affects everyone, it is upon all of us to resist the destructive attempt of multiverse scientists to pollute science by mixing multiverse science together with genuine science.
Let's sum up the past two episodes' argument against the multiverse from the scientific and philosophical methods.
Multiverse scientists claim that the multiverse is science, when in fact it deviates fundamentally from the tried and tested scientific method. By calling it science, they misleadingly imply that it should be accorded greater validity and esteem than it truly deserves.
In fact, multiverse is not science, but a philosophical theory used to explain away our universe's incredible fine-tuning, design, and order, and the poor philosophical theory at that. As we explained in last episode, its failure as a good philosophical theory is based on 3 points. 1. Fine-tuning, design, and order of one universe certainly don't indicate an infinite number of randomly chaotic universes. On the contrary, they indicate an intelligent cause of our one universe. 2. While one can try to use an infinite varied, naive multiverse to explain away fine-tuning, it's a theory of the gaps that can similarly be used to explain away anything and everything. And finally, 3. To rectify the problems of a naive multiverse, scientists must posit unjustified ad hoc measures. The problem is that all intuitive measures don't work, and any contrived measure they hope to find will itself be fine-tuned and designed.
In conclusion, neither the multiverse nor the speculated measure that governs its probabilities are indicated by any observations. Not only is multiverse not science, it's bad science-based philosophy.
This concludes our attack against the multiverse. But we're still not done. Here's why. Our first series showed that the fine-tuning of the constants, design of the laws, and ordering of the initial conditions indicate the existence of an intelligent cause of the universe. So far, this series has demonstrated that the primary alternative explanation, an infinite varied multiverse, isn't a good scientific or philosophical explanation. But there remain 3 scientific attempts by ardent opponents of multiverse to explain either fine-tuning or the initial conditions without an intelligent cause.
In the next episode, we'll discuss Lee Smolin's theory called cosmological natural selection. This is the only theory that attempts to explain fine-tuning of the constants without either an intelligent cause or a multiverse.
After that, we'll examine the theories of Roger Penrose and Paul Steinhardt, which don't address the fine-tuning of the constants, but only attempt to explain the Big Bang's incredibly low entropy conditions without an intelligent cause or a multiverse. So stay tuned.